10 years ago, when I was about 16 or 17, and when I was just starting to learn about engines and educate myself about engine design and machining, I always wondered, what type of engine would an engine builder build for themselves? And today, I have answered that question. The parts I'm about to show you and the engine I'm about to show you, again, are is going to be my personal engine for my land speed Corvette that I race at standing mile events. This engine, I'm not kidding, I ordered the first part for 3 years ago, around July, summertime of 2021, and that was the engine block. And now, 3 years later, all these beautiful parts are here, laid out on this table, and I'm gonna take you through all of them in this video. Again, this is gonna be part one of a multi-part build series. I'm going to go super in depth. I'm gonna do everything on camera. Normally in our standard build series videos, there's a lot that goes on in the background that you guys don't see. All the checking, all the clearancing, all the mock-up helps the video kind of flow together, and it makes it a little easier for me to film in the shop. But with this engine, I want to document every single step for you guys. Okay, let's start with the block. Now, at first glance, looks like a normal LS block. Obviously, it's manufactured by Dart. It is a cast iron block. But as we start to move closer, you guys will start to see some differences in what makes this block so special. Let's start high, and then we'll work our way low. The block is machined and cut for top fuel hoops. Basically, this engine's gonna run a copper head gasket, of course, and in the cylinder heads, which I'm gonna show you guys in just a second, a little sneak peek, there are some hoops that are cut and inlaid into the head. Those hoops are gonna mesh and fit inside this groove on the block and crush the copper head gasket down. It's the same style hoops that everyone runs on Pro Mod, Top Fuel style engines, hence the name Top Fuel hoops. Second, we are running a bushed 904 Chrysler design lifter. Now the lifters are going to be solid roller. Standard Chevrolet design is a .842 diameter, but the Chrysler design is a 903, 904, 905. It's multiple different people in the industry use different terminology, but basically it's a larger diameter lifter that lets you put a bigger wheel on the lifter with a bigger axle, and it makes everything stronger. Let's roll the block over, and that's kind of where the fun starts. So this is Dart's SHP Pro 2 block. It's non-skirted, so I'm gonna run a really trick billet spacer to space up the oil pan. But the big deal is that it has a Ford Cleveland main journal. So this is an LS engine that's gonna run a Ford spec crankshaft design, basically. Your standard LS main journal is 2.559 across. Ford Cleveland is 2.75, it's 2.75, so it gives you a bigger main journal on the crankshaft, which then increases the overlap of the crank journal and the connecting rod journal. And that little bit of overlap where those two journals have overlap is what gives the crankshaft its strength. Just so you guys know, everything in this engine is designed and engineered to operate at about 3,000 horsepower, turning 9,500 RPM. I really can't believe I'm saying that, but that's what this engine was designed to do. I'm not kidding. Apart from the block, technically the block has a part number. Every single part on this table is one-off custom just for this engine. And at the end of the video, I'll kind of talk about the roadmap of how I design and spec and build this engine and what parts are, picked first to determine what we end up with as the end product. So, super trick block. I think I waited 2 years to get it, and then I had to then send it out to get the top fuel hoops cut and some other trick machining done. Really cool. So again, it's got a big Cleveland main. It's also can only be ran as a dry sump engine because we're gonna run a Jessel belt drive, which I'm about to show you next, on the front of this. Normally on an LS, the oil pump bolts to the block right here, and then there's an oil feed passage right here to deliver oil into the motor. As you can see, there are no bolt holes drilled for a pump, and there's no oil feed passage. Oil will be fed into the block through this 10 AN port in the back out of my dry sump oiling system. All right, let's talk about the crankshaft. This is a Sonny Bryant crankshaft. It's fully center counterweighted, it's fully polished, it's an amazing piece of engineering and art. This crankshaft is fully balanced, yet there's not a hole in it. So the way they balance this is they basically will mill on a lathe, or maybe it is just a Bridgeport style CNC mill, but they mill the counterweight down to remove material instead of drilling it. And I'm not kidding, the theory behind that is the holes will scoop oil as it's rotating in the engine, and that can cause drag and windage on the crankshaft. To also combat drag and windage, every counterweight has this knife edge, so it can literally cut through the oil with less resistance. Crazy stuff. The stroke on this crankshaft is 3.75. That with my 4.125 bore is going to give us a 400 cubic inch LS engine. You can see all of these big slugs in it. Those are tungsten Mallory bob weights. There's 1, 2, 3, 4, 5, 6 in the front. 7, 8, 9, 10, 11, 12. There's 12 pieces of tungsten to make this crankshaft balance where it needs to. And of course, we're running a factory 58X reluctor wheel that has been welded to the crankshaft so that at 9,500 RPM, making 3,000 horsepower, it stays solid and we have a strong timing signal. The reason I went with a 3.75 stroke crank instead of a 4-inch stroke crank to build a 427 is because I wanted to bring that rod stroke a little bit closer, this rod journal closer into the center line of the crankshaft. Again, we're increasing this overlap between the rod journal and the main journal right here in the crank. That is where a crankshaft fails at really high horsepower and really high RPM. So there's the crankshaft. Let's move then. I'm gonna go in order of engine build. So actually let's do camshaft first, because that's usually the first part I install. This is gonna be a huge turbo engine that I am gonna street drive. So it is 262 on the intake duration, 268 exhaust duration on a 116 straight up. There's no advance built into the camshaft because we have almost unlimited adjustability with the Jessel belt drive to make the timing advance whatever we want to. So we'll play with that once we get the engine on the dyno with turbos to kind of tweak our RPM curve of the motor. And valve lift is right around 3/4 inch, 0.758 intake and 0.748 exhaust. This is basically a drag and drive style engine build. It's meant to put a lot of street miles on it, but it can still handle serious hardcore horsepower whenever it's time to turn up the wick. So the valve train is fairly stable as far and fairly gentle as far as the actual lobe design on the camshaft is concerned. Yes, it's got a lot of lift, but it's not an all-out drag race camshaft that's just slamming the valve open as fast as physically possible, because I would like to get at least 5,000 miles before I need to put a set of springs in the cylinder heads. So camshaft, crankshaft. Next would be the belt drive. So this is a Jessel belt drive system. You basically have a belt instead of a chain that connects the crank to the camshaft. And there's a lot of reasons for this system. One, the belt actually dampens a ton of harmonics throughout the internals of the engine compared to a chain, which can pass some of them back and forth into the cam, out of the crank to the cam. Second, tons of adjustability. So you can see I can go 10 degrees retard or 10 degrees advance on the cam timing to dial in the torque curve exactly where I want it for my RPM range. Third, if you ever want to change camshafts, you can leave the timing cover installed on the engine, and all you do is you pop off this piece, and then you can slide your cam straight out of the block without having to take off timing cover, balancer, any of that stuff. So again, just as a combination that's new and might need a different camshaft, if the cam specs are too far off in left field for me to dial it in on timing, super easy to change camshafts, get a new one in there and get back on the dyno and see what it wants to do. Bearings, we're running a standard, well not standard, there's nothing standard about it, but it's Clevite's highest grade race bearing. It's their H series bearing that's fully coated. Again, it's for a Ford Cleveland engine, not an LS main bearing. And the rod bearing is a Clevite V series bearing, not an H or a P. This is a bearing that was basically designed for heavy load applications. And so again, because this is going to be a land speed engine, it's going to see that extreme load for a long time. In a drag race engine application, this engine could easily go, you know, I'm just talking horsepower wise, obviously not car or traction or chassis setup. This would be a low 7-second engine, but it's such a short duration, whereas this engine is going to be making that power for a very long duration. So I want a heavy load designed bearing. For the rings, I'm running a high tension oil ring because I want to do everything I can to keep oil out of the combustion process. Whenever oil enters the combustion process, it effectively lowers your octane rating. Now this engine is going to run methanol fuel, so it's not too big of a concern, but I want to do everything I can to keep oil out of the cylinder. And because it's going to be a massive turbo engine, I'm not really relying on a super lightweight oil ring package that might free up a couple horsepower if this was a naturally aspirated combo. For the second ring, I'm running a ductile iron Napier, so it has a hook in the second ring to physically scrape the oil off the cylinder wall, super trick. And for the top ring, I'm running a ProMod tool steel, I think it's an M2 tool steel total seal ring. So super hard alloy, very high heat resistant characteristics, and all in all, just pretty much the best of the best there is for ProMod style engines. Really quick, I'm gonna circle back to this belt drive. ATI Racing, if any of you guys have a belt drive on an LS, ATI Racing makes this front hub that has a key that splines into everything right here. And then they make this bracket that bolts across the motor like that. And boom, you have a cam sensor that reads 4X pickup on your Jesel belt drive system. So I'm going to run a 4X cam and a 58X crank, so I can use a pretty simple standard Holley Dominator ignition system without having to worry about going with crank triggers, and just, you know, it kind of opens up the door of ignition stuff. Connecting rods. Again, these are full custom CP Carrillo connecting rods. I went with a 6-inch length, right? A little bit shorter than most LS engines run. My theory behind it, and all of this is just my theory, I don't have a PhD in engineering, it's just what my theory, what I believe in will help this engine survive the longest, is I want to go with a little bit shorter of a rod than standard because I want to stack up a lot of material in the piston to give it as much support as possible. And I also believe that a little bit shorter of a rod will be a little bit stronger than a really long rod that has to support itself and support a piston way up here and the crank down here. A shorter rod should be a little bit stronger. For example, or just to kind of give you guys a sense of how beefy these rods are, because on camera they look just like a standard H-beam, but these actually weigh the same as our 632 6.7 inch long H-beam connecting rods. So it might look simple right here, but the actual material thickness throughout this guy is insane. And these are going to run the CP Carrillo Custom CARR, C-A-R-R, connecting rod bolt, which is again the best rod bolt available on the market in the aftermarket engine, you know, kind of world. The alloy of the rods and the crankshaft, they will not tell me what type of steel this is, so I'm going to call it unobtainium, because even as myself, the customer, and an engine builder, CP and Sonny Bryant won't say what these rods and crankshaft are made out of, which I just find kind of cool. I don't know. Pistons, full custom JE. So these are, you can see how tall they are, and I believe that that extra skirt will give it more support at super high horsepower than running a really long rod with a really short piston. They have a little bit of a dome on them because this engine will be 12-to-1 compression, because it's going to run methanol at the racetrack and then E85 on the street. It has lateral gas ports throughout the top ring gland, and the lateral gas port, basically, as expanding gases come around, they will trickle into these gas ports, go behind the ring, and pop it out to seal it even firmer. Of course, they have their gold thermal barrier. They have skirt coatings. They have double pin oilers. So like your standard piston, you can see them right here. Standard pistons will just have a single pin oiler. These have duals, and basically it just gives the wrist pin a little bit extra lubrication, which is always good. Speaking of wrist pins, these are pretty much as hardcore as they get for a small block. They're still 927 diameter, but they are 1/4 inch thick. Standard, like just your normal street motor, will have a 0.150 thick wrist pin. These are 0.250. They are H13 tool steel, and they are DLC coated, diamond-like carbon coating. And you find this stuff in, I think, NASCAR and Formula One were the first guys to start DLC coating wrist pins. And so this engine's got them. A really cool feature about these pistons, though, is they actually don't run a lock to retain this wrist pin in the piston. Normally, you would have a little groove cut in your piston, and you'll have a lock, a circlip or a spiral lock or something that you pop in there, and that ring fills into that key, that groove, and that's how it retains the wrist pin. This piston system runs a button, and that's, oh, I'm sorry, taking y'all off camera. That's what these guys are. And so I'm gonna have a button on each side of the piston, just like that, and these will ride against the skirt of the engine block, the sleeve of the engine block, and retain the piston wrist pin between them. These are 2618 aluminum, which is the same material as the piston, and they have about a 5/1000ths of play of what they can kind of wiggle back and forth in between the block. Really cool. And the theory, or the reason for that, is we're giving the piston as much support as possible with all that force and pressure pushing down and just crushing the piston. This button is going to give it a little extra strength right here where it needs it. So I think that's really trick. Put those away. These are the lifters. These are, I don't remember the exact model number, but these are Jessel's baddest lifter that runs a link bar. The only lifter above these are the keyway lifters. But these are, again, they're a 904 diameter lifter. They have a bronze bushing inside of them. And of course, they are fully DLC coated. Really, really trick pieces. Valve train is going to be handled by a steel T&D machine rocker shaft system. So this one tool steel shaft will bolt down to the cylinder head, and then all of these steel full roller rocker arms then bolt to the shaft, just like so on these studs. And then you can get behind it with your lash adjuster and set your valve lash. Cylinder heads are from BES Racing, Tony Bischoff Racing, and these are a huge oval port custom power adder specific LS cylinder head. They are roughly designed and based off the LS7, but their valve placement is completely different. The spark plug placement is completely different, and of course it runs a huge oval port compared to your standard square port on an LS7 cylinder head. These flow at like 800 lift, I think somewhere in the neighborhood of 450 CFM. Of course, they're running a big dual circle track spring, of all things, if you can believe it. And of course, titanium retainers. They have a massive titanium intake valve and then Inconel exhaust valve. And now you can see that top fuel hoop that is cut and recessed into the cylinder head. So that hoop will crush the copper into the groove of the block to fully seal everything up. They have softened chambers, which basically means there is a very small 3 or 5 degree cut that's performed from the edge of the bore leading into the chamber to help slow down the flame front. And that's also why the spark plug is actually tweaked a little bit closer to the exhaust valve and out of the center of the cylinder, so that we start the burn somewhere over in this neighborhood, and then it can slowly travel across the combustion chamber. We want to slow it down because, again, it's going to be making around 3,000 horsepower turned all the way up with a lot of methanol fuel in the chamber. We want to keep that burn controlled so we can keep our timing and our tune-up in check. Of course, 1/2-inch head studs, that's pretty standard and common. Intake manifold is a matching ported CID oval port manifold to match that cylinder head. It has 16 fuel injectors provisions because with methanol, it's a lot of fuel, a lot of horsepower. So we're going to run 16 injectors on kill. And of course, it's got a burst panel on the side to protect all these components if I have a massive backfire or something terrible happens inside the engine. So if you're building and designing an engine of this caliber, I want to talk about now the process of building it and how, in what order you select the parts and how they relate to each other. So the first thing you should order or figure out or decide on if you're planning this engine build is the camshaft. You need to start with the camshaft because we need to know what the valve lift is, what the duration is, and the ramp rate of the camshaft. So I guess technically you should figure out your total cubic inch that you want in your RPM range and how much horsepower you want to make, and then go get your camshaft from Comp Cams or from us. Next, you will call a cylinder head company. You will talk to them, you will tell them, this is what I want to do, spec me a set of cylinder heads that can make that happen. That is important because now we need to figure out where the valves are going to be. Where are the valves located in the bore? What is the angle that they are at? How big are they? And of course, since we have our camshaft, we can then spec a valve spring package and a valve length to fit that camshaft. Now that you have your valves placed and figured out, next you will call a piston company, because now we have valve reliefs. We know where to put our valve reliefs. We know the depth the valve relief notch needs to be made because we have our camshaft specs, and you can get your pistons made. Of course, at that time, you will also talk to a piston ring company, whether they are the piston guys or Total Seal like I did, and of course, get your rings at that time. Once the pistons are done in production, they will give you a piston weight. You then get the weight of your pistons, your wrist pins, your buttons or locks, and your piston rings. At that time, you call a connecting rod company. You tell them, hey, Mr. CP Carrillo, I want to make 3,000 horsepower because I'm a 22-year-old kid. And what could go wrong? CP Carrillo then asks you, cool, that's awesome. We can do that, no problem. How much do your pistons weigh? You tell them the piston weight, you tell them how long you want the rod, you figure out all these dimensions right here that you actually had to tell JE, and then I actually messed up a little bit. Once the pistons come out of engineering, they will give you a weight. At that time, CP Carrillo needs to tell you the thickness of the wrist pin of the connecting rod right here and the thickness of the connecting rod right here so that it doesn't interfere with the piston. So these kind of get made in synchrony actually, but once everything is done, you then have what's called a bob weight. And then you call Sonny Bryant and you tell them, hey, Mr. Sonny Bryant, I need a 3,000 horsepower LS crankshaft. And he'll say, cool, we can do that. What is your bob weight? And then you tell Sonny Bryant, okay, I've weighed all my rods, I've weighed all the components of the rotating assembly, and this is the bob weight I want my LS engine balanced to, which is, on my case, 2,211 grams. That number probably doesn't mean anything to anybody unless you know engine building and V8 balancing. I can tell you that is ridiculous for a small block. That is 540 big block bob weight territory. Our normal LS small blocks, we've got a couple laying around the shop right now, they all have about 1,800 gram bob weights. This dude is 2211 because everything is so hardcore and so beefy. And now you've got a short block. Actually, you've got a full engine. You've got your heads, your pistons, your rods, your crankshaft. It'll get balanced. Everything will come in about 3 years' time. And then here we are, finally ready to start building this engine. I'm pretty excited. I literally am not kidding. I ordered this block the summer of 2021 and it got delivered today from BES Racing because I had to get the block and then I had to send it to them so that they could put the top fuel hoops in the block. I don't have that kind of technology here to do that, nor do I know how to do that because we build street crate motors, which don't need top fuel hoops. Because our customers are reasonable and they don't want to jump off a cliff like I do and go way over their head with a 3,000 horsepower Pro Mod engine. So there are all the parts. In next week's video, or the next video I upload, I don't know, might be next week, might be tomorrow, I am going to hone this block in our CNC cylinder hone with the correct ring finish, surface finish, to run these piston rings in this application. That thing is literally like 20 inches tall. It's obsessive. I love every bit of it. So, thank you for sticking around with me as I ramble through and lecture about why this engine is so custom and so cool, because it is. I don't know if anyone has actually publicized on the internet the inner workings of a 3,000 horsepower LS. Obviously people have done it before because this stuff exists and there are engineers who are smarter than I am that know how to make it happen. But I think it's all like your no prep drag racers or competitive drag racers who aren't giving out any information on their engines. I'm not. I just want to go really fast at the Texas Mile and set the overall Corvette record. And this is the engine to do it. And I'm gonna take you guys along the ride while I put this thing together and machine everything and check all the bearing clearance and settle the ring gap and yada, 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 yada. And it's gonna be sweet. Thank you for watching. I'll see you later. I forgot to mention, in case you're wondering what this kind of engine costs me as an engine builder and someone with a 30,000 subscriber tiny little YouTube channel, these parts that you see laid out in front of you, plus the machining I paid for some of the top fuel work and whatnot, about $40,000 my cost. And some of these parts were ordered 3 years ago. So I don't even know what that block costs today because I ordered it 3 years ago.